What architectural challenges do AI-capable robot chips face when running local Elm or Velm inference on humanoid or cobots, and how are they typically solved?
Challenge 1. Weak AI model capabilities, far from practical use.
The first challenge is about the weak AI model capability and far from the practical use. So first of all, the biggest problem lies in AI model performance, right? We have seen all kinds of the visual language action models and the VR models is for short. So on the surface, like they can all combine with vision and language, but their real world performance vary hugely. So even the top tier model often like hit just 0.4 out of 1 or 1 point environmental adaptability. That means it can merely cope with less than half of the real life scenario, and all other models perform even worse. Okay, simply, but today's robot models are seriously lopsided, and they might do okay on the one simple task, but fall short on the most everything else. So what's more, even their strongest ability is nowhere near human level performance. Humans have all rounds of the solid capability, yet currently, robot AI is still far from reaching the large-scale practical applications. So most fancy demos just work on the control setting, so they cannot just handle complex real-time job at all. This is one challenge.
Challenge 2. Poor hardware-software coupling, tough edge deployment.
The second challenge is about the hardware and software coupling, right? So robots are mobile devices, so they face strict limitation on size, weight, and power consumption. So AI computing units, batteries, parts have to fit into one robot and robot bodies. That create a lot of the troubles. So let's talk about the computing power first. The most advanced chips, just like such as 1000 TOPS, which is already the standard of the standard level of the auto driving system. But the humanoid robot is still really with a far more complete environment and interactive task than the cars. So if you add more high performance GPUs to boost the computing power, and the robots will become very heavier and use more electricity and push upon the overall cost sharply. And that form victory cycles. High-end hardware cannot widely deployed due to the weight, the power, the cost issues. So with limited high performance, software model can never run on their full potentials. It's a huge bottleneck for this.
Challenge 3. Severe data shortages, restricting iterations and upgrades.
The third, we have the fundamental bottleneck, insufficient high-quality data. Like all AI models rely heavily on massive real data for training and improvement. So right now, robot data collection is totally out of scale. Unlike autonomous driving, which has millions of vehicles gathering data around the clock every day, and the most robot team can only rely on a small number of teleoperators to collect data, and the total data volume is tiny. So besides, lots of collect data are very low quality. For example, using the ordinary camera or simply some of the single device to record daily action cannot provide valid data for complex tasks. Take the clothes folding demo as one example. Most of videos can only show folding easily iron and short of t-shirts. No model can rely further on the very complex and crumpled t-shirts with complex steps so far. So lack of real rich data directly slow down this progress. That's why no company so far can build a truly powerful robot system right now. Though many new data service startups have to really pump up to grab this market, and the overall data shortage remain the biggest barrier holding back this whole industry.